To be here on Data Science Dojo, and today I'm going to talk with you about fine-tuning and low-rank adaptation. This topic is very popular in these days, related mostly to generative AI. So let's start with the agenda. At the beginning, we will talk about the regions of low-rank adaptation, which is LoRA. From now on, we will call it LoRA. And what is the problem definition? Then we will see the mathematical intuition behind the process of fine-tuning. And then we'll dive into the algorithm or technique which called singular value decomposition, SVD. The reason we are diving in is because it relates to the LoRA, the way LoRA operates in some way. Then we'll see algorithms, fine-tuning algorithm and fine-tuning algorithm with LoRA, and we will compare them. After that, we'll see some use case where LoRA was applied, and we will see the results, and we'll compare them with fine-tuning without LoRA and with LoRA. And finally, what we will see is that sometimes we can do fine-tuning with LoRA actually without training. And lastly, there are the key takeaways and obviously a Q&A session. So let's start. This is a brief topics that people, if you remember it from your studies or you doing it day to day. So this is something that required to understand what we'll speak about, but don't worry if you not exactly remember each topic. I will provide intuition, and I will provide additional explanations. So everything started with a paper by several researchers from Microsoft in 2021. They came up with a low-rank adaptation technique for fine-tuning. So this paper is basically 26 pages. It describes the principles of LoRA, how it operates. It shows the ways how it reduces the problem of fine-tuning. And now let's talk about fine-tuning. Basically, so if what you see on the screen is basically the schema for like intuition, mathematical intuition behind what's going on when we do fine-tuning. So fine-tuning is basically we can look at it as a model. It can be one of the LLMs, for example, and every model is basically a neural network. So, and every neural network can be represented in a form of matrix that contains weights and parameters. That's a high-level presentation. So obviously, when we are dealing with large language machines, we have a huge matrix. So on another side, we have data sources, documents, everything that we want to integrate into the knowledge of large language model. So large language model is universal. Usually it's universal machines that understand and know everything. But despite that, there are many fields in the world that large language machines are not exactly aware about. So if we will dive deep into discussion with these machines, with the LLMs, we will see that they can hallucinate or provide inaccurate information. So obviously, we would like to update them. But since there is no straightforward update mechanism, the fine-tuning techniques basically comes to solve it. So if you have some information, domain-specific, and we want to fine-tune our LLM with this information. What's going on is that this information represented in the form of embedded vector. So how we get embedded vector? There is an embedded algorithm, usually integrated with LLM, but not always. Sometimes it can be standalone embedded algorithm, like, for example, Word2Vec or FastTech or SIBO, SchemGram, which is the types of Word2Vec models. And finally, we get embedded vector. What is embedded vector? It's basically the vector that contains numbers that represent the meaning, the context of the text that it comes from. So, and this vector usually a high-dimensional vector. It can have 100 plus, 1,000 plus rows, but it's usually one row all the time. So as you see below, we have two things here. On the left side, we see the matrix that represents our large language model. And on the right side, we see an embedded vector. So basically, we need to do some kind of operation between them, so we can find, so we can say or we can see that our matrix W is fine-tuned, basically updated. So what are the use cases basically when we are trying to do so? You can see on the right a few use cases. It's just selected examples. Obviously, there are a lot of use cases, but some of them, one of the popular, where we want to fine-tune our LLM in order to have question answer more accurate, more precise on specific topics. So for that, we need to have new text, new information. We need to have some sort of labels, if you want, not necessarily, but sometimes. In case of sentiment analysis, it's pretty much reasonable that we will have some labels. For example, our LLM knows and understands a lot of things, and if you will ask them, the machine, what is the emotion of this text, probably he will provide a right answer. But this under the consumption that this text is very well known by LLM. What if we provide to LLM some kind of information, maybe anecdote, or maybe something else, something that he is not aware of, or like he is aware but not deep enough in order to understand latent humor, for example. So, and we will ask to provide a sentiment. The model can give us wrong answer. So for that, we have this text, we have the label, correct label of the text. We can segment this text, separate it into a lot of batches, and it's up to the user and up to the use case to decide. And then we perform a kind of iterative training on this large matrix, having our vector, embedded vector, and we creating the loss function, and then we every time we're trying to minimize this loss once we see that our LLM is good enough, and then we stop it, and then we have a fine-tuned LLM. So basically, we are not altering the original matrix. We basically create another one, which is kind of the original, but updated. So all the parameters and weights are updated, and then we can use it for our purposes. Another example is last one, the knowledge integration. Knowledge integration is when we are not expecting from large language model to get some kind of label or some kind of grade or evaluation of emotions. All we want to do is just our LLM just will be comprehended with particular information. For example, we can take some utopic case in astrophysics, something that LLM is not aware of or aware on the high level. And we can embed this text, document, or even book into our LLM, by doing fine-tuning, and then our LLM will know it. But since we don't have labels here, and we don't expect from our LLM to provide us some kind of great scales or evaluation of emotions, we don't need training. We just need to fine-tune it once. So my point here is that we have basically two big scenarios. One, when we fine-tune using iterative training, which is the most common case. And the second case is when we don't need to train, we just need to perform fine-tune. Okay, so once we know and understand that we have on the left side matrix W, on the right side embedded vector V, we understand that we need to do something between these two in order to fine-tune this matrix. So we did not talk about how to do it, and I continue, and later on we will see how to do it. So now I'm going to show you what LoRA is about, the main architecture of LoRA. But before I explain it, I want you to understand that LoRA comes to solve some problem. And the problem is fine-tuning. So what is the problem with fine-tuning? Fine-tuning is a great operation. It's everything okay with it. But it has limitations. What limitations? We deal with large language models. We deal with a huge dimensions of the matrix. Once we do fine-tuning, it takes a lot of time and a lot of hardware resources to accomplish it. And what does it mean? It means that we need to update all the parameters of the large language model. Even those kind of parameters that we don't need to update, we are going to update them. That's fine-tuning. And imagine yourself, we have billions of parameters in a large language model. So every parameter must be updated. So this is exactly the problem with fine-tuning. It's time-consuming, it's intensive from computational point of view, and LoRA comes to solve it. So now I will explain you what LoRA is all about. LoRA contains two major components. One component is something that related to some kind of rank and two matrices A and B, which we will talk about them later further on. So, but the purpose of this rank and this matrices that yet we don't know what it is, but the purpose is to approximate our matrix W, just approximate, create approximation. And the second component of LoRA is, in fact, to perform fine-tuning with iterative training, but in this case, we will update only limited amount of parameters, not all the billions parameters, but only limited amount of parameters, and we will get the same result as if we were updating it without LoRA. So LoRA comes and solves a really tough problem, and this is what's LoRA all about. So in the first component is basically reminds like LoRA employs the principle of singular value decomposition. We will see how it works and understand what LoRA does. And the second part is basically we benefit mostly from the saving time by fine-tuning when we do backpropagation. So while we do iterative learning, training, we know that we are going forward and backward, forward and backward. So every time we go backward, we need to update our parameters. Why we need to update parameters? Because we want to minimize our loss. And the process of updating parameter is very consuming. Since we need to update much less parameters than in usual case, that's where benefit of LoRA comes into action in the backpropagation. So now on very high level, we know what LoRa is and that the LoRa contains basically two major components. Let's see what's going on. So what's going on with this singular value decomposition? What's inside this that LoRa takes and uses it? Once we understand what is singular value decomposition, from now on we will call it SVD. We will understand how LoRa manages to reduce number of parameters. So SVD is kind of algorithm that he gets the matrix, and what it does, it finds three matrices: matrix A, matrix B, which is a transpose of matrix A, we'll see it, and matrix Z. So matrix Z is a diagonal matrix. Matrix A, left orthogonal matrix, we will see it on this schema, and matrix B, which is a transpose of the left side, we call it right transpose matrix. So this algorithm tries to find such two matrices and the third matrix, which is diagonal matrix, which basically dictate the dimension of matrices A and B. What does it mean? That means that matrix Z is basically diagonal matrix. Diagonal matrix contains only values on its diagonal, and everything is zero. So this algorithm generates such a matrix that each value on its diagonal, it calls singular value. This is a terminology, singular value. So each singular value has the property of being larger than the previous one. And you can see that sigma 1, which refers to singular value, are larger than sigma 2, and sigma 2 larger than sigma 3, etc., etc. So we can conclude, obviously, now that the last value in this diagonal is the smallest number. So what does it mean having this number? What's the value of the single value represent? So it represents its impact on the information. Impact on the information of the new matrix that we will create by multiplying A by Z by B. So initially, in original matrix W, we have a huge amount of these singular values, a lot. So this algorithm, what it does, it reduces, just remove the single values on the diagonal, obviously from the end, because on the end, they are less impactful on the information. And he finds the optimal number of singular values to remove in order to retain the information existed in the original matrix and not lose vital information. But on the same side, on the same time, to reduce the dimensionality of new matrix that will be created. So the smaller diagonal of the Z, the smaller matrices A and B will be. So if we talk about a huge matrix W, we can come up with small matrices A and B and diagonal matrix Z. So if we multiply them together, we will get a matrix W tag, what you see, which will be approximation of the original matrix. So this is a great idea, and this is like a very powerful tool. Imagine to yourself, you get the matrix that much smaller than original, but it contains almost all information that in the original one. So let's continue. Let's see basically how it works. So you here see example 5A is basically the example for a matrix. Suppose we have a matrix 1, 2, 3, 4, 5, 6. Just a high-level example. So how we find a rank? What is a rank? Rank is basically another word to say number of singular values. So if we have diagonal of 5 singular values, we can say this matrix, the rank of this matrix is 5. If we have a diagonal of 6, the rank is 6. If we have 2, the rank is 2. So how we find this, basically? So we take this, this is like theory, like formula. We take 5b, we take this matrix, given matrix, we multiply it by the transpose of itself, and then we get some other matrix, which is, in our case, 3 by 3. And the dimension of this matrix is basically the rank. So if we get 3 by 3, so in this case, we will have rank 3. If we would get much bigger matrices, then we'll get bigger ranks. And you obviously maybe ask, what about if it's not square matrix? What if it's 3 by 4 or 10 by 20? So we take as a rank the least between two dimensions. If it's 3 by 4, we'll take 3. If it's 3 by 5, we will take 3 by 5, we will take 3. So this is a way how we can get, this is just example, how we get rank. But having a rank is not enough. We want to understand what are the values of the singular values. We want to know what's values. So how we do it? So if you look at the 7 below, this is a formula. This formula tells us, take your W multiplied by transpose W, subtract some lambda, which we call, which in mathematics called eigenvalue, and multiply it by I. I is identity matrix. Is everything is 0, only 1 on the diagonal. So if you solve this equation, then you will get your eigenvalues. You will find them. So, but what is eigenvalues? What is the meaning of eigenvalues? The meaning of eigenvalues is that the values are basically depicts how, if we do some transformation, so they like a scale of transformation. This is geometric intuition. But in our case, if we take square root out of eigenvalue, we will get the value of singular value. And that's what we're looking for. So in this example, you can see that if we take our matrix, which is resulted by W multiplied WT, minus this eigenvalue multiplied by identity matrix, which we get this matrix like 0, 0, and on the diagonal lambdas. And we solve this equation, we calculate the determinant and solve the situation, we will get eigenvalues. And as a result of it, 6, we will find what our singular values. So once we know our singular values, once we know the rank, the number of singular values, the algorithm of SVD, we are not going into this algorithm. I'm just explaining the idea. He, by optimization, finds such A and B, so if they will be multiplied one by another, including this diagonal matrix, we will get good approximation for our original one. So this is about SVD. So LoRA uses this principle to reduce the rank of the matrices. While you reduce the rank of the matrices, it's like you reduce your diagonal in the matrix. So your matrix becomes smaller. The LoRA uses this approach. So let's continue. And let's see how it looks in terms of the algorithm. Okay, so on the left side, you see the traditional fine-tuning. What is traditional fine-tuning? It's like fine-tuning without LoRA. What we have here is an algorithm and just a numerical example. Suppose our matrix W, which represents our LLM, has dimensions 1000 by 300. If we multiply one by another, we'll get 300k. So then we define loss function. Then we define the optimization algorithm, which will minimize this loss function. And we see y hat and y is basically y is our ground truth, the labels that we have, and y hat is a prediction that if we ask from LLM to predict what is the, like to tell us what's the emotion of this text, that will be y hat. And then we start training. So training contains two parts, forward pass and backward, and update parameters, which is the core of idea here. So what happens usually is multiplication. We take this matrix W, which represent our LLM. We take the embedded vector, which represent our document or documents or even book. We multiply them like multiplication of the matrices. And this operation is time consuming and there's a lot of operations there. Meanwhile, don't look at the numbers of operations. Just omit it. We will look at them when we see the right side, and then we will compare. Then once we calculated this new y hat, then we basically calculate the loss function. And based on the loss function, we are doing backpropagation, and we are updating our parameters. So the next time, our loss will be less. So this requires two things: computational of gradients, and then actual updating the matrix. So to calculate gradients, we do it on an entire set of parameters. And updating the parameters, we do it on the entire set of parameters of matrix W. In our case, it's 1000 by 300. But you can imagine what it looks like when we deal with Claude or Grok or Gemini or ChatGPT or whatever. You imagine what the dimensionalities are. So once we finish the updating, we are going in the loop again and again, until our loss is good, like no loss, almost no loss. And then we finish. So now let's try to understand how many operations we did here on this side. So if we look at the 6, we see that this is matrix multiplication. Matrix multiplication takes basically two operations: multiplication itself and addition. So what number of multiplication do we do? It's just the dimension of our matrix, which is 300k. What number of additions we do? The same. So in total, we have 600k operations. Operations are the flops. These flops, that's how it defines in the computer. So let's see what have we in the line 8, which is a red line. Why a red line? Because here we start to feel the intensity most of all. So it's the same. We have 3000k things to compute for, and which is another 600k. And then we're going to update all the parameters we have, which is again 300k. So basically, we have here three times 600k, which means almost 2 million operations. And remember, this is per one iteration. Okay, so what is the green? Why all this operation in yellow and one is the green? The green is, I'm just mentioning here, that we are dealing here, in our case, with 300k parameters. Okay, so far so good. Let's see what's happened when we do it with LoRA. So with LoRA, we see the following. First of all, the input is the same, except of matrices A and B and rank. So as previously we understood that LoRA employs the principle of SVD and can find, given the matrix W, it can find matrices A and B and the rank 10, which is the dimension of these matrices, okay? So that it gives good approximation to our original matrix W. Okay, so once we get it from the component number 1, we get into component number 2, the algorithm and training. So basically, we like init matrices A and B. We're actually not initializing it. We already calculated, so we have it. So we define the loss function as in other case. We define optimization algorithm. Again, the same story. And then we go into the loop of training. And we go into the forward path. What happens in the forward path is different from what happened on the left side. So we create some kind of delta W, which is a result of multiplication B by A. Why B by A and not A by B? Because if you look at the dimensions of the matrices, if we cannot multiply A by B because the dimensions are not fit. So we multiply B by A. Then what we do, and this is very interesting, we take the original matrix and we add to this, not multiply, we add this product, this multiplication that we've did. So basically, like we're saying, okay, B and A, they are approximating, they are good approximated of our origins. So let's take to add it to the original matrix. We will get the W tag, and this will serve us as good approximation. And the next step is we have Y hat. Basically, we use the same multiplication as in the left side, which is heavy. And once we calculate it, we get a loss function. And then we go backward. And again, we compute gradients per each parameter. And finally, we are updating the parameters. But in our case, what we are updating is not 300K. In our case, we see that our dimensions of our matrix A is 10 by 1000 and 300 by 10. So basically, we have here 13K. So we have 13K parameters only to update. And this is marked by green. But let's look at the operation in the yellow one. So here on this side, because in forward pass we do much more than on the left side, here we have something very different. Multiplication B by A creates a huge amount of operations, 6 million operations, because it's 10 multiply 1000 multiply 300K, only for multiplication, then for addition. So if you look at the overall operations, number of operations, we get almost 13 million operations. In contrary to the fine-tuning without LoRA, which has almost 2 million operations. So you may say, what is the deal here? LoRA comes to resolve our problem, not to increase by times the number of operations. The answer is like, this is not about operations. This is about parameters. How much parameters do we update? Because update one parameter requires a certain amount of operations. So if we have a lot of parameters to update, eventually our 13K parameters will compensate in terms of operations something that's going on the left side. So what we see here is basically two things. One thing is that LoRA employs SVD, creates approximated matrix, and by that, reducing the dimensionality of approximated matrix. And as a result of that, we have much less parameters to update. And second, we see that number of operation is not a deal here. We don't care about number of operations. Okay, so let's see when LoRa beneficial and when not. So in systems like question answering, it is beneficial because we're doing iterative training, and we saw the algorithm just now. So it's clear. The same with sentiment analysis. And by the way, with automated context generation, if we want that our LLM will generate proper context based on the right knowledge, so we also can train it. But when LoRa is not beneficial, LoRa is not beneficial when we do not need to do training. For example, like knowledge integration. If we want just to integrate knowledge into LLM, we need to perform one fine tuning, and that's all. In that case, LoRa is not beneficial because LoRa becomes beneficial when we do it iteratively many times. So in one time, it's not beneficial. And another case when it's not, basically it's not applicable even, is when we have embedded algorithm standalone. What does it mean, standalone? Every LLM comes with integrated embedded algorithm. But as I mentioned at the beginning, there are several standalone embedded algorithms like word2vec, fast text, even BERT can be used for that purpose. So in this case, it's not really applicable because of the technicality point of view. We will not going into that in this lecture. So let's look at the practical use case. What you see is this experiment details is the information about my laptop and the memory. And what I used GPT-2 for this experiment. And I used sort of sentiment analysis for Reddit posts. So I collected 10K. It's not large, but just for to show initially 10K posts, and I trained GPT-2 in two ways. One, like I did fine tuning for that in order to see the results, and second, I did it with LoRa. So what did I get? I have here three aspects. One aspect is memory usage, second is model size, and third is CPU utilization. So as you see, in every one, LoRa is winning. But the problem here is that when you look at how much it's not twice, it's not triple, it's just approximately 20% better. And you may ask, why only 20%? Like, it's not, maybe it's not good enough. So, the reason is that the fact is that it's not always the same proportion. So it depends on a lot of things. It depends on the number of iterations. It depends on your model. It depends on the local machine you're working on. It depends on many things to get different proportions in benefits. So in this case, obviously, there is a benefit, but not such benefit that we can say, wow. Okay, so this is about some use case. Now, I want to show you a little bit, extend the horizon and tell you that LoRa was born in 2021 by Microsoft. But since then, there is such a progress in everything that has to do with low rank adaptation. What does it mean, low rank adaptation? We already understood that rank is the size of diagonal, which basically is the dimension of the matrix, approximated matrix. And low is basically low. We want to lower it, to make it lower, but not lose information much. And adaptation. What does it mean, adaptation? Meaning that we are adapting to this approximated matrix and updating only a limited number of parameters. And you see here the variation of this idea. Everything is like research. Everything has its paper. The reason I'm showing you it here is just you to know that LoRa is not something that final solution and the only one. And that's not all. Here I, in addition, like another several variations, but there are two that I want just to mention a little bit more in detail. Let's look at sparse LoRA. Sometimes we have matrices that are sparse matrices that are mostly contain zeros. So that will impose some certain kind of mathematical problems if we will do exactly what we just saw before with LoRA. So there is another variation of LoRA that takes into consideration the sparse matrix and provide the solution accordingly, proper solution. Another one is distributed LoRA, something that really amazing. You can do this idea, what we've just done today, and fine tuning with LoRA, but using distributed computing. So we can even make it even more efficient by parallelizing the tasks, the operations, and the very process of approximation. But this is not so trivial because LoRA should support this parallelism, and the original version of LoRA does not support it. So this another one. And also there is an online version of LoRA that can perform everything that you saw, but online. Every calculation it does it on the fly in real time. Something that imposes really tough mathematical problems, but there is a version of it, and even GitHub for that. Okay, so what are our takeaway? Key takeaway. So we saw that LoRA has mainly two components. One, using the principle of SVD, and second, reducing number of parameters as a result of it in backward pass. Second, we saw that efficiency metric for LoRA is not the number of operations, but number of parameters it's working on. Also, the speed and computational resources that when we use LoRA is not always the same. It can vary. And nobody guaranteed to you that you will always get twice or triple or 10 times better results. It's very variable. And finally, as we saw right now, there is a lot of versions of LoRA, a lot of variations of LoRA, something that shows how progress not only in that direction, but in every direction happens. This is amazing. And now we have 15 minutes for questions, but let me just take another few minutes, and I want to show you what's happened when we are not training, when we do fine-tuning without training, just by fine-tuning without LoRA, what happens? So in fact, what we do is we have our W matrix, represented LLM. We have our embedded vector V. So we want to get updated LLM. So updated LLM is W new. So what? But this going like the ways to do it is to come up with some transformation, multiply by embedded and add it to the original matrix. So what kind of transformation, how to find it is another story. Below you see 3 ways to calculate this transformation. I'm just showing you so you know that this exists. Second option to do a fine-tuning without training is to create a tensor product between embedded vectors and multiply it by some scale alpha. So tensor product you can see below, it looks like this, and then you just add 2 matrices, and then you get your original matrix. Much simpler because it's only one time. And finally, another option is to take our original matrix of LLM, to take embedded vector and do the following. For every column in our original matrix, we will compare it with the column, only one column with embedded vector, and the comparison with cosine similarity, and we will write down the score. And we do the same per each column in our original matrix. Finally, we will have the vector of scores. So what we do, we multiply this vector of scores by embedded vector and add it to the original matrix. So this is like 3 ways of doing so. And by that, I'm finishing the lecture. You see my QR code. This is my LinkedIn. I'm very active on LinkedIn. I publish posts writing a lot about everything, much in depth. So you are welcome to join. And let's look what questions do we have. So I have questions. I have a question from Ataliba. Is fine-tuning essentially a result of a customized dataset trained analyzing the loss function and accuracy on a much bigger model or matrix, right? Let's say GPT-2 or Llama, right? That's you correct. That's exactly what's going on. And we saw it. So if our matrix was not such has such huge dimension, so maybe we won't need the LoRA for that. But when we talk about ChatGPT-2, it's unimaginable number of parameters. This is huge matrices, and fine tuning basically can be done with something big and something small. Otherwise, it does not make sense. You want to fine-tune something by a small piece of information, and this something must be big. If it's small, so maybe what you want to fine-tune is bigger or contain more information. So this is not like, it's always something big and much smaller. Okay, we have a second question here by Juan. How does LoRA compare with other types of fine-tuning, like DPO, direct preference optimization? When would you choose one over another? So I did not personally perform the comparison between these two approaches, but I can say that it's really depends on amount of, in our case, on amount of text or data we want to fine tune. For example, we can have one document and we can represent it by one embedded vector, or we can represent each paragraph in this document with one embedded vector, or we can have several documents and per each we can take embedded vector. Finally, and when we have many such vectors, we can create a batch and do it. So it really depends on how we structure this information that we want to fine tune with the big one. So I'm mainly concentrated on the part of on the smallest part and not on the biggest one. Unfortunately, I cannot tell exactly the percentage of how it behaves, and if I'm not mistaken, the competition between both can vary. So sometimes one can be better than another. It depends on the case. Okay, we have another question regarding the use of LoRA on sparse matrices. How much reduction on the accuracy of the model? Okay, great question. What about the impact of LoRA on the accuracy of dense matrices? Okay, so basically now, if I understand correct, we want to understand the accuracy that LoRA provides in two cases. One case when we have sparsity, and the other one when we have density. So it's so when we have the density, that means that we don't have any problem with lacking parameters or gapping in something. And that means that we will get as much accuracy as we can. Obviously, it will be a much intensive rather than on sparsity, because sparsity we have lags, missing holes, and a lot of things. And the way how we can compensate, we basically losing information. So especially when the sparsity comes as a result of something not good. Not as because if you trained your model, for example, imagine yourself, you train your home ChatGPT. So you create LLM, which basically can be represented by matrix. And what if your matrix is sparse? So what happened? What could possibly can happen that you have a lot of sparsity? So mainly the sparsity problem comes when you do some operations on something original, like original matrix, and you get some output, and this output has some sparsity as a result of some certain kind of operations. And then on this type of matrix, you perform fine-tuning. So to answer this question, in summary, when we have the sparsity, we tend to less accuracy. If we compare it with original, you call it density matrix, so original matrix, that everything okay with it. We have a potential loss of not loss of information, as a result, loss of accuracy. Okay, so any other questions? Someone? Yes. Juan asked the question, when would you choose fine-tuning with LoRA versus using RAG? Oh, okay. So basically, I prepared some slides that elaborate, explain when you explain what, but I didn't put it in this lecture because I thought we should focus only on LoRA. But RAG basically what it does, we kind of doing workaround with lack of knowledge in our LLMs. So we utilizing vector databases sometimes. We using some kind of retrieval algorithm, etc., etc. So we are doing a lot there. But what we try eventually to do is to get the results that are updated and correct. So if we do LoRA with fine-tuning, we will get much better results and in much less operations in terms of activating databases, using the retrieval mechanism, etc., etc. So basically, this one aspect, when if I care about the precision and accuracy of something that I'm doing, I probably will go to fine-tune rather than using RAG. But on the other side, and also, if you have few documents or few information, so fine-tuning is better. But if you have a lot of documents, maybe books, then perhaps RAG, even then, RAG suffers from this kind of retrieval and indexing problem. So I would say that vice versa, even if you have important information that in terms of a lot of chunks, so better run these chunks as a batches through fine-tuning with LoRA rather than using RAG because of this kind of indexing and retrievals. But if you have something very particular, small, like a piece of paper, a page, 2 pages, maybe RAG in that case would be simpler to use because I don't think that the results would be much different if you take 2 papers and using it through RAG or you're using it through fine-tuning LoRA. The differences will be slightly. We will feel it only when we have a big amount of information. Yes. Another question. We have another few minutes to go. By the way, regarding the LoRA, it depends which type of LoRA you are using. There are a lot of types of LoRas. So sorry, RAGs. So it also depends. Some type of particular type of RAG might be better than to perform fine tuning rather than using another type of RAG. Yeah. Okay, so maybe at the end, I want to say that the reason that I delve into the mathematics here and these particular details is that there is a lot of misconceptions around fine-tuning and LoRA and many other very popular terms and approaches. People maybe know how to use it, how to call them, but they don't know what stands behind. And I think this is very important to understand and know what stands behind, because once you know it, you can customly change it, edit it, better understand the problems you have with the results, to feel yourself more comfortable, be more inventive, maybe, make more sensible research, etc., etc. So it's always preferable to understand nuts and bolts behind this. Maybe one more question at the end. Someone? Okay, I see that there are no more questions. This is one.
Yeah, Danny, if you can just check your chat, there are a few questions there as well. From Jason,
okay.
regarding the use of LoRA on sparse matrices, how much reduction of the accuracy of the model? What about the impact of LoRA on the accuracy of dense matrices?
Yeah, that's something that I already answered, but there is another one. Which part of the model is LoRA used? So if you're referring to the model, our original model, that like LLMs that we want to fine tune, so it basically uses a back propagation, backward pass. That's where they update much less parameter due to the previous steps. That's where we see the benefits of that. I hope I understood your question right. So yes, I see the questions. I got them. Another question is, what is the best way to choose fine-tuning method for our data science? There are many options available. How do we know which is the best? First of all, fine-tuning methods. It depends on the problem you're trying to solve. There is no ultimate solution to say this method is better. How you can do it? You can do it experimentally. You can see the results, initial results on the previous experiments that you did, and to see the proportions of differences and see the tendency, and based on that. But there is no algorithm that you can use to identify fine-tuning. It's a lot of variables that depended on this decision. Obviously, the experimentation would be most harder way, but most prominent way to understand it.
Thank you, Danny.